In this video, we're going to think about dynamic games. So we're going to think first about a game where there are two periods, period 1, period 2, and then we're going to stretch that out a little bit and think about a little bit longer games. If you think back to some previous videos that we've done, we looked at the Cournot model and we looked at the Bertrand model. And in both of those models, you've got two firms, but there's only one time period. So in the Cournot model, your two firms are each choosing their output simultaneously. And then in the Bertrand model, your two firms are each choosing their price simultaneously. So it's a one-period game. What we want to do now is we want to consider the possibility that there are two time periods where one firm gets to make a decision in the first time period, and then the second firm is going to react to that. We're going to see what ends up happening in terms of the profits of the firms and the quantities that result from that. What we're going to do is we're going to think about a model that was first put forward by an economist, a German economist named Stackelberg. So it's the Stackelberg model of duopoly. And then again, after that, we're going to think about repeated games or even games with more than two players. So let's start by thinking about the Stackelberg model. And the nice thing about the Stackelberg model is that the setup is exactly the same as the Cournot model. So we've got a market demand curve that looks like this, P equals A minus B times Q. Now we're going to think of firm 1 as being the leader. So firm 1 gets to act first. And then firm 2 we'll think about as being the follower. So firm 2 is going to make their decision after they see what firm 1 does. Each firm is going to have a constant marginal cost equal to C, just like we've been doing. And the total quantity that's produced in the market, which we're going to call Q, is going to be equal to the quantity that firm 1 produces plus the quantity that firm 2 produces. So the same thing as the Cournot model, except for this part. In the Cournot model, they choose their quantities simultaneously, and then the outcome is revealed. Now firm 1 is going to choose Q1, and then firm 2 is going to react to that. Now firm 1 knows that firm 2 is going to respond to its choice of Q1 with its best response. And when we were working through that with the Cournot model, we talked about a response function. So firm 2 is going to respond. It's going to make its best decision in terms of what output to produce based upon the quantity that firm 1 chooses. So that is how firm 2 is going to react, and firm 1 knows that that's how firm 2 is going to react. Let's take a look at firm 2's response function, best response function. We derived that back in our Cournot video. So remember, we've got, if we plug this quantity in into our demand curve, our inverse demand curve, we've got A minus B Q1 minus B Q2. Now we're taking the point of view of firm 2, and from the point of view of firm 2, remember that chunk, those two things right there, are the intercept of the demand curve that it faces, or the inverse demand curve. So what we're interested in is firm 2's marginal revenue curve, because firm 2 is going to equate marginal revenue and marginal cost, and so marginal revenue for firm 2 is going to be the same intercept, A minus B Q1, minus twice the slope, so 2B times Q2. There's the marginal revenue curve for firm 2. We set marginal revenue equal to marginal cost. Marginal cost is C, so we set this equal to C, and if you work through the algebra of that, what you're going to get is firm 2's best response function, and it looks like this. It's A minus C over 2B minus Q1 over 2. So we derived that back in our Cournot chapter. Now firm 1 knows that what this looks like. It knows that it can think through the process and understand that firm 2 is going to respond to firm 1's decision with this quantity. So if we think about the demand curve now that firm 1 faces, we can plug that in for Q2. So now we know that the demand curve that firm 1 faces is P equals A minus B Q2 minus B Q1. And from the point of view of firm 1, this chunk is the intercept, but we know that firm 1 realizes that firm 2 will respond with its best response, which is given by that. So we can plug that in. I'm going to plug that in. It's equal to A minus B times that. A minus C over 2B minus Q1 over 2 minus B Q1. Now, the algebra of this is easy to work through. Go through and distribute that B through, and then you've got to get a common denominator over here, a common denominator over there. If you do that, I'm going to skip the algebra for the sake of brevity here, but if you do that, here's what you're going to get. You're going to get A plus C over 2 minus B Q1 over 2. So that's the demand curve that firm 1 faces. Notice now that algebraically we've eliminated Q2 from this. We've incorporated firm 2's response function into the demand curve faced by firm 1. And so now we can solve this problem. What we need, of course, is the marginal revenue curve for firm 1, and that's equal to A plus C over 2 minus twice the slope. Now the slope here is B over 2, so when we multiply that by 2, it's going to cancel out. We're going to get minus BQ1. So there's the marginal revenue curve for firm 1. We obviously want to set marginal revenue equal to marginal cost, so we set this equal to C. Again, I'm going to skip the algebra, but we would set this side equal to C and then solve for Q1. We would get this. Q1, the optimal choice of Q1 for firm 1 is going to be A minus C over 2B. That's the quantity that firm 1 is going to choose. And they're going to lead with that quantity. Now, we also want to know, well, how is firm 2 going to choose its quantity? And we already know that. Given this choice in the first period by firm 1, firm 2's quantity, if we plugged in this right there, did some algebra and solved for Q2, what we would get is this. I'm going to skip that. Q2 star is going to be A minus C over 4B. So this would be the quantity that the leader would choose to begin with, and then in period 2, firm 2 would respond by producing that quantity. And you can see that really we could think about this as 1/2 times A minus B over C. And we could think about this as 1/4 times A minus B over C. So what you can see from this is that firm 2 is going to end up producing half as much as firm 1. If you multiplied this by 1/2, you would get that. Now, total quantity in the market is just the sum of these. And if you add those up, the algebra is simple, but if you add those up, the total quantity, which would be Q1 star plus Q2 star, that is equal to 3 times A minus C over 4B. There's the total quantity produced in the market. Now, if you were to go back and review the Cournot video or look at your notes on that video, what you would see is that the quantity from the basic single period Cournot model looks like this. I'm going to call it QC for the Cournot model. Let's actually call this QS for the Stackelberg model. But the Cournot quantity is this. It's 2 times A minus C over 3B. So now let's think about how these compare. What we can see is, again, if you think about this term over here, A minus C over B, what we've got is 3/4 of A minus C over B. And over here, we've got 2/3 of A minus C over B. So this number is bigger. In other words, the total market quantity produced with the Stackelberg model, where one firm moves first, ends up being larger than the total quantity produced in the Cournot model, where the two firms choose their quantities simultaneously, a single period model. Once you know this market quantity, then all you have to do is plug that into the market inverse demand curve and you can get the market price. I'll skip the algebra of that, but the Stackelberg price that ends up emerging would be this, A plus 3C over 4. If we compare that to the Cournot model, let me just put it in a little box here. The price from the Cournot model was A plus 2C over 3. What we end up with is a situation where the quantity in the Stackelberg model ends up being bigger than with Cournot. Consequently, the price with the Stackelberg model ends up being lower than with Cournot. Now, let's kind of think about some points that need to be discussed. One of them is that even though these firms are identical, right, the firms have identical cost of production, because firm 1 moves first, that gives it an advantage. So we would say this is a first mover advantage. And that first mover advantage shows up in the sense that if you calculate profit here, which would be relatively easy to do, you would take the price minus cost of production and then multiply it by their quantity that they each produce. You'll see that the leader ends up producing or earning a higher profit than the follower, which is not surprising. They get to move first, they have the advantage. Let me also point out that if you were given a demand curve, like say P equals 500 minus 2Q, something like that, where you knew what A was and you knew what B was, and you were given a marginal cost of C. If you had numbers for A, B, and C, then it's a simple matter to plug in A, B, and C into these statements and find out what the quantities are that are produced. In other words, you don't have to work through this every time, setting marginal revenue equal to marginal cost. But I always tell my students that if you're ever unsure what to do and you're working through a firm problem, the first thing that you should consider is marginal revenue has to be equal to marginal cost. So you need to figure out what marginal revenue looks like, and you need to figure out what marginal cost looks like, set them equal, and then out of that should emerge the choices that the firm is going to make. Let's talk about one other point, and that is that it's kind of ironic in this model in the sense that for firm 2, if you go back to the Cournot model, where the two firms choose their quantities simultaneously, each firm has incomplete information. And so what firm 2 has to do is they have to say, okay, well, let's think our way through this and figure out how firm 1 is going to respond to what we do. And then given that, what's it in our best interest to do? And so it has incomplete information. Here, in terms of firm 2, there's no incomplete information. For firm 2, there's complete certainty about what firm 1 is doing. And yet, even with complete certainty, firm 2 ends up doing worse than when they had incomplete information. So it's ironic in the sense that you would think that having complete information allows you to improve your situation, whereas here it doesn't. And of course, that boils down to the fact that firm 1 is getting to move first, and that is an advantage in this model. Now, let's think about taking this 2-period model where one firm gets to move first, and let's think about that if instead of choosing quantities, the firms were choosing their prices, like with the Bertrand model. So let's think about now sequential price competition. Let's start by thinking about the firms choosing price, but firm 1 gets to choose their price first, and then firm 2 gets to choose its price second. And let's start by thinking about a situation where the two firms are producing identical goods. Well, in that case, firm 1 is going to be able to reason its way through this thought process. Firm 1 is going to say, okay, if we choose anything greater than C, marginal cost, then firm 2 gets to observe what we chose, and they can undercut it just a little bit, and they can capture the entire market because the goods are identical. So in that situation, you get the basic Bertrand outcome that firm 1 is going to realize it needs to set its price equal to marginal cost, and firm 2 is going to follow by doing the same thing. So that's not very interesting. It becomes more interesting if we think about the goods not being identical. So if you go back and you look at the Bertrand video, towards the end, you'll recall that we talked about what happens if the firms produce differentiated goods, and we used that hoteling spatial model to figure out what the result of that is. So let's think about this. Let's think about firms choose price sequentially. Firms choose price, and the goods are differentiated. And let's go back and kind of review the setup for that spatial model that we talked about. So what we had was we had a situation where we have firms, two firms, and we had firm 1 down here at an address of x equals to 0. So here's firm 1, and we had another firm out here at x equals 1, and that's firm 2. A location, our consumers are spread out evenly along this 1 mile segment, and we can think about any particular position on here as being an address, an x. So if we've got an x at 1/2, that means half of our consumers are over here and half of our consumers are over there. Our consumers are identical, and we would represent the value that they place on the good with V. That's their reservation price. And they all have an identical reservation price, but they differ in their position. And remember, we can think, it's easiest to think about this spatially in terms of your distance away from a store, but it doesn't have to be that. That's the genius behind Hotelling's model, is that we can think about this as attributes of a product. And so we can think about a consumer who is right here and has preferences for this product, but it's not exactly the product that they want. And this product is even farther away from their desired preference. So it's a more useful model if you think about it in terms of utility and the utility cost that you incur because you have to consume a product that's not identical to the ideal one for you. If we're thinking about a consumer and they consume this product right here, then the cost that they would bear, the utility loss, remember was T times X. That's if they consume over here. And if they consume the other one, it was T times 1 minus X. Now, let's, in this problem where we have firms choosing price, firm 1 is going to choose its price first. And firm 2 is going to choose its price second. Remember in the simultaneous model where they choose at the same time, what ends up happening is we found that marginal consumer, and we saw that everybody to the left of that would buy from firm 1, and everybody to the right of that would buy from firm 2. And where that marginal consumer was, whether they were down here or in the middle or up here, depended on the price chosen by firm 1 and the price chosen by firm 2. If the price chosen by firm 1, as it goes up, that moves our marginal consumer more to this direction. Or excuse me, more to this direction. A larger portion of the consumers would buy from firm 2. On the other hand, as the price of firm 2, as P2 goes up, then that moves the marginal consumer in that direction, and a bigger chunk of consumers buy from firm 1. Okay, now we're thinking about firm 1 choosing its price first and then firm 2 choosing its price second. We're still going to do the same thing. We're going to identify that marginal consumer. Now the marginal consumer is the consumer the consumer who gets the exact same amount of consumer surplus from consuming good 1 as they would get from consuming good 2. Okay? And so what that looks like, remember that consumer surplus from buying good 1 was the value they place minus the price that they pay for good 1, also minus the utility costs that they bear, which is T times XM. And I'm putting M there to indicate the marginal consumer. So this is the marginal consumer if that consumer surplus is equal to the consumer surplus that they would get from buying good 2. And that would be, the consumer surplus would be the value that they get, what's left over after we subtract off the price they pay for firm 2's product minus the utility cost that they bear. And that utility cost was T times 1 minus XM. So that is T right there. And so what we're doing is where the marginal consumer ends up being, where XM is, depends on the choice that firm 1 is going to make and consequently the choice that firm 2 ends up making. And then once we know where XM is, all the consumers to the left of that buy from firm 1 and all the consumers to the right buy from firm 2. So XM ends up being the portion of consumers that buy from firm 1. If you solve for this, if you do the algebra to solve for XM, here's what you're going to get. XM, the address of the marginal consumer, which depends on P1 and P2, is equal to P2 minus P1 plus T over 2T. Now, what we can do then is we can figure out the demand curve that's faced by firm 1. Let me say that the process we're going through here is very similar to the process that we went through here. We want to know how firm 2 is going to respond to the choice of price by firm 1. So essentially, we just need to come up with the best response function for firm 2, and then firm 1 is going to use that in its decision. So that's the process we're going through here. But in order to do that, we need marginal revenue curves, which requires us to get demand curves. And that's what we're doing here. So the demand curve faced by firm 1 which is a function of the price of good 1 and the price of good 2, that is equal to this portion of n. So remember, this is the number, the proportion of consumers who buy from firm 1. So we just, and there are n consumers, so it would be P2 minus P1 plus T over 2T multiplied by n. Likewise, for firm 2, the demand curve faced by firm 2 would look like this. It would be 1 minus that, and you're going to end up getting P1 minus P2 plus T over 2T multiplied by n. We can get firm 2's best response function from that. And what it's going to look like is this. P2 star indicates that it's its best response function. The best choice of P2 is equal to P1 plus C plus T over 2. Now, firm 1 knows that this is how firm 2 is going to respond. Firm 1 is going to choose P1, and then firm 2 is going to respond by looking at this. It's going to be the price that firm 1 chooses plus marginal cost plus this utility cost that consumers pay. Divide by 2. That's the price that firm 2 will choose. So firm 1's demand curve now, we know we can plug in P2 here. Firm 1's demand curve becomes this. Demand curve facing firm 1 ends up being P2 star minus P1 plus T over 2T multiplied by n. Ignore that V that's right there. There's the demand curve that firm 1 faces. If you do a little bit of algebra, plug that in. Here's what you're going to get. You're going to get that the demand curve faced by firm 1 is equal to n over 4t c plus 3t minus p1. So there's the demand curve that firm 1 faces. Remember, what we need is the marginal revenue curve because we need to set marginal revenue equal to marginal cost. So what we would need to do is we just simply need to invert this. We need to solve it for P1. So here's a quantity, right? That's Q1. And we're going to solve that thing for P1. If you do that, you're going to get, so I'm going to say invert. What you would get would be P1 equals C plus 3t minus 4t over n multiplied by Q1. That's the inverse demand curve that firm 1 faces. Now we need marginal revenue. And that's simple because marginal revenue for firm 1 is this term right here. That's the intercept, right? C plus 3t. Minus, we need twice the slope. Well, here's the slope. If we multiply that by 2, it becomes 8t over n times Q1. There's marginal revenue. We can set that equal to marginal cost, which is going to be just C. So if you set marginal revenue equal to marginal cost and you solve, I'm going to skip that, Q1 star ends up being 3n over 8. So we know the quantity. What we need is the price. So we need to plug that into the inverse demand curve for firm 1. When you do that, what you're going to get is P1 star equals C plus 3t over 2. So firm 1's going to set that price They're the first mover. They're going to choose this price. Once we know that, we can simply plug that into firm 2's best response function, which is right here, and solve for the price that firm 2 would respond with in the second period. What you get is that that price is equal to C plus 5t over 4. Notice that firm 2's price is a little bit lower than firm 1's price. This is C plus 6/4 of t, and this is 5/4 of t. It's a little bit lower. So that's exactly what we would expect, right? Firm 2 moves second, and what do? Well, they undercut firm 1's price by a little bit. But now here's the thing that makes this different. The goods are differentiated, so that means that firm 1 does not lose all of its customers. Having a differentiated good means that you can raise your price a bit and not lose all of your customers, even though the other firm has a lower price. So what happens is firm 2 ends up with a slightly larger market share. Let me also point out this. Remember T represents the utility cost that the consumer gets or incurs because they have to consume a product that's not the exact product that they would like, the ideal product. And the bigger T is, the bigger these prices are, or let's say the further away from marginal cost they are. It's actually easier to think about it the other way. If we reduce T, as T goes to 0, both of these terms would go to 0 and prices would go to marginal cost. T represents how different the consumers believe the goods are. So if the goods are very different, we would expect these prices to be very different from marginal cost. But if the goods are not very different at all, then that means consumers incur no utility loss if they choose good 1 over good 2. It doesn't matter. And so then the prices would go to marginal cost, which is what we would expect, right? We saw in the Bertrand model that without product differentiation, price equals marginal cost. So that's intuitively satisfying. If you go through and you compare profits in this game to the simultaneous game with differentiated goods, what you're going to see is that in this case, both of the firms are better off. But now notice what's happening here. Firm 1's better off than the simultaneous move Bertrand game. Firm 2 is even more better off than firm 1. So both of them are better off, but it's firm 2 that is benefiting the most from this. So what we're seeing here is now there's a first mover disadvantage. Firm 1 has to commit to a price, and then being able to move in that second period allows firm 2 to undercut it a little bit. And because the goods are differentiated, firm 2 steals a little bit of market share, not a whole lot, but enough that it's better off than firm 1 is. What we want to do now is we want to think about games that have maybe more players or more time periods, and we want to use that to think about the credibility of a threat to enter a market, or maybe the credibility of a threat to try to keep a firm from entering a market. So I need to clear this off, and then we'll come back and take a look at that. So the thing that makes the sequential game different from the simultaneous game is that firm 1 is making a credible commitment in period 1 to some strategy. Either they're picking a quantity, they pick a quantity, or they pick a price, and it's done. What we need to do now is we need to think about the issue of credibility. So a firm may make a threat to do something, to try to achieve an objective. And so what we need to think about is, well, so how credible does the other firm or the other firms believe that that threat is? Once you start thinking about dynamic games, what you realize is that a dynamic game that has multiple time periods is going to be made up of a series of smaller games. We call those subgames. So a one-shot game is a single period. A two-shot game or a two-period game would be like two one-shot games. And once you think about that, we start to have the need to think more carefully about what we call an equilibrium. And there's a concept known as subgame perfect or subgame perfection that we need to think about. I'm just going to say subgame perfect. So let's talk about what it means for a strategy to be subgame perfect, or a set of strategies, an equilibrium to be subgame perfect. And what it means is that if you have a strategy chosen at the beginning of the game, for that to be optimal, it must be optimal to stick with that strategy at every stage of the game. So if at some point in the game you reach a point where you think, oh gosh, now we need to change, well then that strategy was not subgame perfect. So a subgame perfect strategy means that it's the right strategy at every subgame. And we'll look at an example of that here in a second, and I think it'll become obvious what that means. Let's think about a two-stage game between two software firms. And what we're going to do is we're going to think about firm one as being what I'm going to call the incumbent. They're the firm that's already in the market. Okay, they're established in the market. Firm two, we're going to call a potential entrant. This is going to be an upstart firm. Upstart firm wishing to enter the market. So the firm two is going to be deciding, it's the entrant that's deciding whether to enter or not enter. And then firm one is going to react to that. So let's think about firm two's options. So firm two can either enter or stay out. Firm one, the incumbent, the firm that's already in the market, is going to be choosing whether or not they allow the firm to enter, whether they accommodate firm two when they enter, or whether they fight. Okay, so firm one's options they are going to be to accommodate or fight. And by fight, what we're talking about there is, let's suppose firm one says, look, you better not enter the market. If you choose to enter the market, here's what we're going to do. We're going to slash our prices, and it's going to hurt us, but it's going to hurt you bad too. And so if you enter, that's a dead end. You might as well just stay out. Okay, so firm one's got to decide, do they make that threat and then do they stick by that threat? Do they actually fight, actually slash their prices? Or if firm two decides to enter, do they just say, okay, well, now we've got to share the market? Now, there's more than one way to look at a problem like this. We're going to start with the not so good way to look at it. We're going to look at it through the point of view of the game matrix, which we've talked about before. So a game matrix, we've got two players. I'm going to put firm one up here. Here's firm one. That's the incumbent, right? And then we're going to put firm two over here. This is the firm that's looking to enter. And so firm one can either fight or they can accommodate. And firm two is either going to enter or stay out. Now what I'm going to do is I'm going to divide these cells in half, and I'm going to put the payoff for firm one up here in the top corner, and I'm going to put the payoff for firm two in the bottom corner of each cell. let's suppose we think about this cell to begin with. This is the cell where firm 2 enters the market and then firm 1 decides to accommodate. Let's suppose that in terms of the profit that they get, that they each get 2. That could be billion, million. That's not that important. On the other hand, let's suppose that firm 2 enters the market and firm 1 slashes their prices, and then that leads to 0 profit for both of them. And then let's suppose that if firm 1 decides to stay out, well, then that means, or excuse me, firm 2 decides to stay out. Well, that means, so firm 2, let's pretend like they have they're in other markets. They're deciding whether to enter this market, but they're in other markets. And if they don't enter this one, they would earn, let's say, 1 profit. And it doesn't matter if they're not entering the market. It doesn't matter whether firm 1 fights or accommodates. Firm 2 is just going to get the 1 billion in profit from the other markets that they're in. And if firm 2 stays out, that leaves firm 1 as the only firm in this market. Let's suppose they get the monopoly profit, which is 5. So now let's think about Nash equilibria. So if we go through here, let's start with this cell right up here where firm 2 enters and firm 1 accommodates, right? So let's think about firm 1 entering. Well, that means that, or excuse me, firm 2 entering. We're in this row. That means firm 1's either going to have 2 billion or 2 or 0. They'd rather have the 2, so they don't regret their strategy. And given that we're in this column, firm 1 or firm 2 is either going to get the 2 or the 1, and it would rather have the 2. It wouldn't desire to change its strategy and get the 1. So that's a Nash equilibrium. Let's think about this one up here. So this is a situation where both of them, the firm 2 has entered and firm 1 fights. Do either of them regret their strategy? Does firm 1 wish that it had accommodated? Well, yes, actually it would. It's not going to be happy with that because it sees that it gets the 0. It could have had the 2. This can't be a Nash equilibrium. If you go through it, you'll see that one can't either. But now let's consider this one, the combination of firm 2 staying out and firm 1 fighting. Well, so that means that firm 1 has chosen to fight. That means that firm 2 was either going to get the 1 or the 0. They wouldn't desire to change from this. And then if we think about firm 2 as staying out, well, firm 1 is going to either get 5 either way. So they wouldn't desire to switch away from this because that's not better. So it turns out that's a Nash equilibrium. There are 2 Nash equilibrium in this game. If we look at it this way, what we're going to see is that one of them, this one, is not subgame perfect. We'll talk about that. So we've got these 2 Nash equilibria, but let's talk more about this one because there's something that's not very satisfying for that. And that is that firm 1 would never actually have to fight if firm 2 stays out. It's really relying on the threat that it's going to fight, hoping that that threat would keep firm 2 out of the market. So we have to decide, well, is firm 2 going to treat that threat from firm 1 as being credible or not? Is it a credible threat? And it turns out that firm 2 is going to be able to reason their way through the fact that firm 1 is probably not going to stick by that threat to fight. And the reason is that if firm 2 enters, then firm 1 does better by accommodating. It's a non-credible threat. So what we need to do is we need to rule this out. And this really points out why looking at this game in terms of the game matrix is not the most useful way to look at it. But this is really where subgame perfection comes in. It turns out that this is not a subgame perfect outcome. Let's use what's called the extensive form of the game. extensive form. This gives you a better feel for the dynamic nature of the game. So I'm going to put a little dot down here, and we're going to put firm 2 here because firm 2 is making its decision first. Firm 2 is going to decide whether to enter or stay out. And let's represent the two choices that firm 2 can make with two branches here. So this is going to be enter, and this is going to be stay out. We call these little dots here nodes, but right up here, if firm 2 stays out, well, that's the end, right? So right out here, that's essentially the end of the game, and that's where, if firm 2 stays out, it's going to get 1 in profit. That's going to leave firm 1 as the only firm in the market, and it's going to get 5. So I'm going to put the payoffs this way. I'm going to put the payoff that goes to firm 2, I'm going to list it first. And then this is what firm 1 would get. So this is our new entrant, this is our incumbent. Now, if firm 2 enters, that leads us to a node where now firm 1 is going to make a decision. And its decision, it's got two options. It can either choose to fight or it can accommodate. And so right here, this is firm 1 making a decision. Okay, so I'm going to circle that firm 1's making a decision there, firm 2's making a decision at the beginning. Now, if firm 2 chooses to enter and firm 1 chooses to fight, then we get these payoffs. Each of them gets 0 profit. On the other hand, if firm 2 chooses to enter and firm 1 chooses to accommodate, then we get each of them splitting the market and getting 2 in profit. So if we're thinking about subgames, then this is a subgame. There are actually 2 subgames here because we always consider the full game as a subgame. So here's a subgame, and then the full game would be a subgame. So for something to be considered subgame perfect, that means that at every one of these stages of the game, it has to be an optimal outcome. And clearly, what we can see is that fight is not a good strategy. In this subgame right here, fighting would be a strategy that would not be chosen by firm 1. Fighting is not a good strategy. So the only subgame perfect outcome here is for this strategy where firm 2 enters and firm 1 accommodates. We get this as the subgame, the outcome of the subgame perfect combination, which is enter, accommodate. And the best way to think about this really is to work backwards. So if we think about being at this node where firm 1's making a decision, well, firm 1 is either going to get 0 or it's going to get 2, and it would rather have the 2. So it's going to choose to accommodate. And so now we've got to think about, and firm 2 would know that. And so now we come back here and we think about this. Okay, so firm 2 is going to either get, by staying out, they're going to get a profit of 1, or if they enter, they're going to get this profit of 2 because they know that firm 1 is going to accommodate. So that means that firm 2's best strategy is to enter. So the easiest way to identify these subgame perfect equilibria is to just simply work backwards. Let's think about one final thing, and that's something that's known as the chain store paradox. So we can think about the situation that would exist if there was maybe more than one entrant. So maybe we've got an incumbent, and that incumbent is facing not just one firm that's thinking about entering, but multiple firms that are thinking about entering. And what we're going to be able to do is we're going to be able to think about this as occurring maybe across different time periods. So let's think about this. Maybe if there are multiple entrants, and let's suppose that what happens is that right now none of the entrants have the resources to enter the market, but as time goes by one, each of those entrants are going to get the resources to enter the market, and they're going to start to enter. They're going to make a decision about whether to enter. And so let's suppose this. Let's suppose that firm 1 decides this. They say, look, here's what we need to do. We need to fight the very first entrant. And then, if we can do that, that'll establish a reputation for fighting, and then that'll keep the other entrants out. They'll decide, okay, well, firm 1 fought in that first period, or maybe they fight the first period and the second period and the third period, and then they get this reputation for fighting, and then that keeps the other potential entrants out. They just stay in their own markets. So firm 1 might think, well, we need to fight early on, and so let's think about whether or not that would be a strategy that would work. Is it possible that by fighting early, they can scare off later potential entrants? So what we're going to do is we're going to think about that last situation first. So let's start by saying, let's suppose there are 20 separate markets. So the incumbent faces potential entry in 20 separate markets. And it's easiest to think about these occurring one after the other. Okay, so let's work backwards. So let's think about the 20th game. So if you think about the 20th game, well, in the 20th game, the last situation, there's no reason for firm 1 to fight, because the only reason you would ever fight is to try to scare off future potential entrants, and there are no future potential entrants. So there's no reason for firm 1 to fight, and firm 20 is going to know that, right? So it turns out that if we can think about this as being that very last 20th game, firm 1's not going to fight. So for that 20th potential entrant, it's going to be enter and accommodate. That gives us the Nash equilibrium. So firm 1's not going to fight in the 20th game. Let's go back to the 19th. So now we've got firm 19 deciding whether or not firm 1 is going to fight or whether or not they're going to accommodate in the 19th. Well, so the 19th potential entrant would be able to work through the 20th situation just like we did, and they would be able to say, well, firm 1's not going to fight the 20th entrant. They're not going to try to scare them off. So there's no reason for them to fight us now. We can all see that you're not going to fight in the 20th. So there's no threat that you would make that's credible. And so the 19th potential entrant knows that firm 1 is not going to fight them. And so enter and accommodate would be the Nash equilibrium for the 19th game. And then we can go to the 18th. And because the 18th potential entrant can work their way through the 20th and the 19th game and see that firm 1's not going to fight in either of those, because of that, there's no reason for them to fight in the 18th game. And so this whole thing kind of unravels. And what you see is that fighting is never going to be the right thing for firm 1 to do. It's not the right move at any stage of the game. And we call that the chain store paradox. And now that's a very simple game that occurs over multiple time periods. And of course, one important consideration that you have to think about is I'm talking about a 20-period game, a finite game. things may be different if we have an infinite game, a game where there's no identifiable end. So we have to think about that, and we'll consider some of that in future things that we look at. It's also the case that this doesn't mean that it's impossible for a firm to make a credible threat. That just means, given the parameters of the game that we've laid out here, no threat that firm 1 makes is going to be credible in this situation. There may be other things that the firm can do, or other situations that may arise where a firm can make a credible threat. So we'll look at some of that stuff later. I'll see you in another video.